Okay, welcome. We'll get started here in just a second. We're continuing in chapter 11 here. Okay, so we been talking about electrons into this chapter 11. We're ultimately going to be talking about really electron configuration. Again, what sort of goes on in terms of energy, we talked a little bit about last time as electrons sort of transition from one energy level to the next, what's happening. And so remember this also, as we talked about in this sort of chapter here, we talked about waves. So waves are, again, ways that energy is basically transmitted in space. And waves have wavelengths. They do have frequencies. We can calculate the energy associated with wave through an equation that we saw. We can also calculate the wavelength through another equation that we saw. So there was a couple of those sort of formulas. Allows us to calculate things like wavelength, things like frequency, which is how many times a wave passes a particular spot per second. And there was that one equation there. Let's get something right with here, maybe. Let's see here. Grab something. So we saw basically a couple important little equations based on sort of waves, which was c is equal to the wavelength times the frequency, c being the speed of light, which is at 3 times 10 to the 8 meters per second. This is the wavelength in meters. The nu there is the frequency, and remember, frequency is basically reciprocal seconds are a hertz, as they both are basically the same thing. It's a one-to-one relationship between a hertz and a reciprocal second. We also talked about you could kind of tie that into energy, which is E is equal to H times the frequency, H being Planck's constant. That's a 6.63 times 10 to the minus 34 joules times seconds is the units. Again, the frequency here being in reciprocal seconds or a hertz. And you can actually put both of those together, which is oftentimes very useful because that allows you really to figure out the energy with all you need to know is sort of the wavelength. So for example, if you went E is equal to H times the frequency, which would give you hc over the wavelength. And again, the nice thing about that, E being energy, H is that Planck's constant, C is a constant. So again, if you just know the wavelength, you can pretty much calculate the energy associated with that wave. And the relationship between sort of energy, wavelength, frequency that we also talked about was that the lower the longer the wavelength, the higher, the shorter the frequency, and the lower the energy. While the shorter the wavelength, the higher the frequency, and the higher the energy that's associated with it. So those were sort of the relationships that we saw as the electrons sort of transition down and as energy is being given off in the form of these waves. They may correspond to different parts of the electromagnetic spectrum that we also saw. Electromagnetic spectrum are places like radio waves, UV, IR, also visible part of the spectrum. That's where we see colors. So that's where we see the red, orange, yellow, green, blue, indigo, and violet. Infrared, X-rays, and then gamma rays there at the end. So depending on sort of what energy level those electrons are transitioning on as to sort of where on that spectrum that we will see something happening. Again, if it comes out in that visible part of the spectrum, we will see colors again, sort of like the fireworks example there. As those electrons transition, they give off that energy in the form of a photon of light, which corresponds to somewhere in that visible part of the spectrum where we do see color. Any questions on any of that sort of stuff we talked about last time? Okay, then I think it's about where we left off. So again, we sort of also are transitioning to this sort of idea, or this idea of energy as electrons either gain energy as they go from a lower energy level to the higher energy level, or as they lose energy as they transition back down from higher energy to lower energy. The energy is thought to be what is referred to as being quantized. And basically what that means is these electrons, for example, will either gain or lose energy, and that's they're going to gain or lose enough energy to make the complete transition from one energy level to the next. So as we talked about last time, they're never going to find themselves kind of between energy levels. So they'll definitely gain enough to go from, say, the first energy level to the third, or the fourth back down to the second. They won't go like the fourth and sit halfway between a couple of different energy levels. So that's sort of the idea of quantized energy, that, you know, energy is sort of gained and lost in what is sometimes referred to as packets of energy. And again, they gain or lose enough energy to make those full transitions. So much like I talked about sort of walking upstairs, you have enough energy to get from one step to the next. You don't usually find yourself, you know, halfway between steps. You don't have enough energy to kind of make it in most cases. All right, so we left off here with Planck, who is the H from Planck's constant. He studied a lot about energy and emission profiles when he heated solids, and he saw that energy was being given off of those solids as it was being heated. And when you do those sort of things, you sort of give energy to atoms. And again, there's a couple different ways you could do that. Very simple way, like a flame test or something like that. You know, like we talked about, when you're heating up water, and sometimes it overboils, it hits the flame. Again, when it hits the flame, all that water and all the atoms in there gain a lot of energy, like those electrons, and they do basically go to a higher energy level. So that's sort of the idea here. Atoms can emit or give off light, but in order to do that, they first has to be excited. So they has to gain a certain amount of energy, basically to go from a lower energy state to a higher energy state. And basically the energy that's released in the form of a photon is what happens as they come back down. So in this example here, this guy here gained enough energy to come up in energy. Much like we also talked about, things in high energy is not really the optimal sort of situation. Things like to be in the lowest possible energy. So eventually this sort of electron is going to want to kind of work its way back down. And again, in order to do that, it has to give off some energy. Again, that conservation of energy. And again, in this particular case, the wavelength of that photon of light that's coming off would correspond to the red light. And obviously a red light would be emitted as this electron is falling back down. So typically what we're seeing a lot of times, especially when we sort of see colors, is as those electrons are coming back down in energy, they are emitting light. And that's what is sometimes referred to as an emission spectrum, because they are basically emitting these things, or this energy, as they are losing energy and coming back down. So there's two sort of states in terms of atoms and electrons, really, and that's sort of an excited state, and that's what sometimes a ground state. And energy states or energy levels are also sometimes, as we will see, abbreviated with the letter N, and is what is referred to as the principal quantum number. And again, it's really a fancy sort of name there for basically your energy level. And N basically runs from 1 through 7 in terms of values in most cases. And when you have N equals 1, that is what is sometimes referred to as the ground state. So that's the lowest in energy. That is the state that is technically closest to the nucleus, and that N equals 1. Typically, anything above N equals 1 is considered an excited state. So N equals 2, 3, 4. So usually we sort of visualize it, you know, N equals 1 is like on the bottom, then N equals 2, N equals 3, and so forth. So as we kind of keep going upwards, we're increasing the energy. Electrons are getting further away from the nucleus because they're higher in energy. Also, they're not going to be held as tightly as they kind of move further away from the nucleus. So when a hydrogen atom absorbs energy from an outside source, it enters an excited state. So again, a couple different, very simple sort of ways you could, like I mentioned, sort of excite an atom, fire or something like that, adding heat or energy. Also, like an electrical discharge tube, you could try an electrical current through it. That's going to excite all the atoms that are there. They're going to gain a lot of energy. And again, what you're really seeing as you maybe witness some light or something like that, or colors, is those electrons going to those higher energy states and coming back down. So when electrons and atoms do receive energy, they go into that excited state, but they do quickly want to get to that lowest sort of stable state of energy. And that is emitting of a photon of light to do that. Again, if something goes higher in energy, in order to come back down, it's got to give off that energy in the form of a photon. And again, that has to do a lot with what we talked about with energy and that sort of conservation of energy. So if something gains a certain amount of energy, it has to release a certain amount of energy. So something around it is basically absorbing, or the surroundings is absorbing all that energy. And here's sort of that picture of it. Again, this would be a ground state energy level, like n equals 1. Maybe this is n equals 2, excited state. And again, our electron, as it coming back down, we see our photon of light. Now, what I mentioned before is that typically atoms are a little bit different than, say, metals and things of that nature, or the sun. There's two types of sort of spectrums that we see when we have these sort of emission spectrums. And two types of emission spectrums. One is a continuous spectrum, and one is a line spectrum. Now, continuous spectrum is kind of like the name implies. Essentially, everybody's coming off all at once. So you get everything happening, all the wavelengths coming off at once, kind of like white light. Everything's just kind of, you got all the sort of levels coming off at once. And that's different than really atoms, and especially atoms in their gas state elements. They will give off what are known as line spectrums. And line spectrums essentially mean that you see these distinct colors of light, or lines, as specific wavelengths that come out. And they're very specific line spectrums for elements. They're so specific, I think is what I'm trying to spit out there. One of those words, whatever. They're so specific there, I'll try that again, that you can actually look at a line spectrum and you'll be able to actually determine what element you're talking about, because each element has its own sort of fingerprint, if you will, in terms of their line spectrum. They have certain colors that come off in terms of these lines. They come off at specific wavelengths. So based on the number of lines that you see, based on the colors that you see, and based on essentially the wavelength that they come off at, you could basically identify it. So if you kind of look at say hydrogen here, which is what we got here, we have an electrical discharge sort of tube. The electricity obviously is exciting all the electrons. We've got all these electrons and hydrogen going up, and then they're eventually going to be coming back down. And what we can see if we look at it through a prism is it will separate out the light, and what we will see is these sort of distinct lines that occur at specific wavelengths. And these lines basically, for example, for hydrogen here, are the four lines that we see occur, and we know, hey, I see the kind of purple line, the green line, or the blue line, the yellow line at these specific wavelengths. I know I'm looking at hydrogen.
It's not P. It's not P. It's like a P.
All right. All right. Any questions on that there? Yeah. And here's sort of what an electrical discharge tube looks like and a line spectrum looks like, I think. Lower, there you go.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
So again, that's a very common sort of spectrum. So all the elements pretty much will give off that sort of line spectrum. And again, like I said, based on those sort of lines that you see, the wavelengths that you see, you could definitely identify it. For example, something like the sun, you shouldn't look directly in the sun, but sometimes the sun, for example, will give off more of a continuous spectrum, you know, wavelengths in all sort of aspects of it. You don't usually see colors if you sort of peek at the sun directly, which you shouldn't really do. But you see kind of like everything's white, right? You can't really see, you know, so you see a lot of that sort of white lights are given off. Also, if you look at like a lights, it's kind of fluorescent lights and stuff like that as well, you'll see more of a continuous type spectrum. More rainbowy, I guess, is the way you could kind of think of it in terms of the colors rather than these distinct sort of lines that you see. So these distinct sort of line spectrums, they indicate that only certain energies are allowed. Electrons are basically in certain energy levels. And what we're really seeing, for example, is sort of this idea that, you know, if we have so for example, we had an electron on the 4th energy level. It went all the way down, say, to the 1st energy level. And again, this is a big transition in terms of energy. So as we were talking about before, this would be probably a higher energy sort of transition. Higher energy would probably mean it would have more of a shorter wavelength. And if you remember, in terms of the visible part of the spectrum, we had red over here, violet on this side. Red is lower in energy, right? Longer wavelength. Violet is higher in energy and shorter wavelength. So if we saw this more longer transition, you know, we'd probably see a color heading towards the violet part of it, as opposed if we saw the electron transition just say from the 2nd energy level to the 1st energy level. That's a much shorter transition in terms of energy. Lower in energy transition should be a longer wavelength, and we would expect to probably see a color more towards the red part of the visible spectrum, you know, if we were able to kind of see the colors. So again, depending on sort of the color that you might see in these sort of emission line spectrums, you could have an idea in terms of the energy and maybe how far that electron is traveling in terms of energy based on, you know, sort of the color and where it is. Any questions on that there? Okay. And so, for example, in hydrogen example, what we anticipate is the different lines that we see as a result of these different transitions. So again, one coming from, say, this energy level down, next one from this energy level down, here and here. And again, this is an emission spectrum because the electrons are dropping back down in energy and emitting this photon of light at that specific wavelength. And so this idea, as I sort of talked about before, this idea of quantized energy gives us these sort of distinct lines because, again, either electron is on this step or it's able to transition fully down to, say, this step, or maybe it's on this step, you know, it's going to stop at this step here. And there's really no stopping points other than, say, that step, this step, this step, this step, and so forth. So you're either, again, on sort of one step or not. In a more continuous spectrum, as you can see, it's almost like a ramp, right? So if you're walking up a ramp, you could decide, I'll just stop here, right? Or maybe I'll stop here, maybe I'll stop there, maybe I'll stop there. And that's why more in a continuous type spectrum, everybody's sort of coming off all at once. And we don't see this really distinct line spectrum like we do with elements, where either the electrons on this energy level, this energy level, this energy level, or they transfer from one energy level to the next. Again, in a more continuous sort of spectrum, we see everything coming out all at once. And you could technically be kind of anywhere along the way. And again, elements basically always do a sort of line spectrum, this quantized energy. So in the context of excitation, an electron in an atom or an ion is identify which one is true. Only specific quantities of energy are released in order for the electron to return to the ground state. So that is true. That's that idea. Quantized energy, again, it's going to lose enough energy to come back down from one energy level to the next. White light is never observed when an electron returns to the ground state. That is true. Again, white light is more of a continuous spectrum, and you would see a whole bunch of different, more rainbowy type of effect occur. Electrons is only excited to a certain energy level. That is also true. Again, as they absorb that energy, same idea. They're going to absorb enough energy to either go up or down, depending on sort of which way, you know, it's happening. So if the atom absorbs the energy, electrons going up, and they will eventually come down. So if you think about, for example, like a flame test, if you take your little guy, you dip it into your sample, then you put it into the flame. Once you put it into the flame, that's the absorption part. All the atoms there are going to gain all that energy. And then very quickly, it will come back down in terms of energy. Again, very much like that example of boiling the water. As you're heating it, it's absorbing all that energy. And then obviously as the water maybe overboils, the actual water that hits the flame gains even more energy. And that's, again, when you see like the flame on your stove, again, go maybe like yellowish or so as the water hits it. Again, all these sodium and electrons in there are basically being exciting. And so this idea of quantized energy really brought up an early sort of model of the atom in terms of electrons, energy, and how they are transitioning. And the idea here is what is referred to as the Bohr model of the atom. We're going to talk about the Bohr model of the atom. Again, it's not correct. It was later proved to be not so right. It works really well to sort of describe what's happening with hydrogen. Works good on hydrogen, but not so good on the rest of everybody else as you move away from one electron. But sort of the idea of the Bohr model of the atom is this sort of planetary model where we have these quantized energy levels, and electrons are traveling around in these pretty little circle or orbits here, as I draw really bad circles to highlight them. But we have these electrons that are traveling either in, say, in this first energy level, second, or third. Again, each of these would be like n equals 1, n equals 2, n equals 3. Again, the n being the principal quantum number or the energy level, 1 being the lowest in energy, as you can kind of see here in this model. And basically the idea here is if we had an electron, say on the first energy level, if it gains energy, it's going to, say, transition all the way up to the third energy level, for example, and eventually it will work its way back down. And it's that part where it's working its way back down that's going to give off that energy of light in the form of a photon that we see for a color. So the idea here is they're just transferring around in these nice little circles about the nucleus. And again, when they gain energy, they go from one to the next and to the next. And as we'll talk about very shortly here, electrons really don't travel in pretty circles like that in sort of a predictable type pattern. And that's why we sort of move away from the Bohr model relatively quickly when we talk about sort of electrons. And so this is the idea there, and this is for hydrogen, for example. Again, that red line that we see in hydrogen may be a result of a transition from the third energy level to the second, as opposed to, say, this more blue line here as is transferring from the fifth energy level to the second energy level. Again, this transition going from fifth energy level to second is more energy levels. Again, would require more energy to do that. And that would also mean that we would see a color, again, closer to the violet side of the visible part of the spectrum, which we do here, which is that blue line, as opposed to this one. This is a very small transition in terms of energy. So smaller in energy. And again, as we can see here, we would expect them closer to that red color. And so his idea here is, again, as they are transitioning these energy levels, the electrons are given off it. That corresponds to our color that we see. Now, his idea here were that these electron are the electrons, since there is only one electron in hydrogen, is moving around from the nucleus in these nice orbits. Again, not going to really move randomly, but pretty kind of easily moving around in these circles. Bohr's model gave the hydrogen atom energy levels consistent with the emission spectrum. Again, as I mentioned before, n equals 1 is considered a ground state. And again, anything above n equals 1 n equals 2 through 7 are referred to as excited states, which again are higher in energy and further away from the nucleus. So as I mentioned before, Bohr's model of the atom was incorrect. Electrons really do not travel in these pretty little circular type orbits. They do travel really randomly about the atom, sort of randomly moving. And as we will see here, not in great detail go into all of it, but essentially there's no really good way to know exactly how a particle like an electron is moving or its location at the same time. So more that you know about sort of one idea of that, how it's moving, the less you know about where it's at and stuff like that. That's, as we will, I think, see, what's sometimes referred to as the Heisenberg uncertainty principle there. The concept of electrons in an atom can occupy specific energy levels is equivalent to saying that energy levels are quantized. So that's that whole idea of this energy is quantized, basically means specific sort of packets of energy. And again, electrons basically gain or lose energy that way in the form of enough to get us from one spot to the next, as we've been talking about. So as we sort of moved away from this idea of Bohr's model of the atom, this sort of planetary model, and that electrons are in orbits, we moved to what is sometimes more referred to as a wave mechanical model of the atom, which involves a lot of crazy equations and calculus and stuff like that, which clearly we're not going to get into any of that. But the ultimate idea here is, and these are some of the guys that did obviously a lot of work on that, Heisenberg, his uncertainty principle, Schrodinger, who basically kind of came up with these sort of probability maps, de Broglie, who basically said, as we will see a little bit about that, you know, waves can have particle-like functions and particles could have wavelet type functions as well. So these guys really did a lot of work to help us move away from Bohr's model of the atom. And as we will see, we will also move away from the idea that electrons are in orbits to this idea of electrons are in what are known as orbitals. And orbitals, as we will see, are really just probability maps, sort of high probability, low probability of where you could find an electron in an atom, again, because they really don't, they're not traveling these pretty sort of circles like Bohr's model of the atom basically suggests. So first off, again, we're not going to get into super much of these. If you ever go on and take physical chemistry, there's a whole first semester of that where you do all these truly calculations of these things. It's fun times, not really. No. But sure, most people wait to their very last semester to take that class. Schrodinger and basically de Broglie, they describe an electron basically bound to a nucleus, and de Broglie was very big on this idea of what is sometimes referred to as a standing wave, sort of like a guitar string. If you pluck it, you can see the wave, but it's sort of fixed in, right? The string can't move anywhere, but the wave is basically fixed in on the guitar as you pluck it, but you can still see sort of the wave move. And that's sort of the idea as to what they sort of thought about as an electron. Again, the idea that it is going to be attracted to the nucleus, right? Because the nucleus is positively charged. So there is that attraction between the positively charged nucleus and the electron, which is kind of going to hold it in place, kind of like the string on a guitar. So it's able to sort of move around, but it is sort of tethered a little bit to the nucleus based on that sort of attraction. So it can't necessarily just float away, if you will. And that's what we sort of see here. This is the idea, sort of a standing wave. We have sort of it locked in on both sides, but again, if you plucked it, you can see the wave form. These guys are sometimes referred to as nodes, and these are things that are have no amplitude. Remember, a wave, right, has an amplitude. It's basically the height of the wave, if you will. So there's certain parts in a sort of a standing wave, obviously, because it's sort of locked into place. You know, there's parts where there's really kind of no amplitude or distance of the wave or height of the wave, and that's sort of important in terms of its relationship to the nucleus and sort of where it's standing. So Schrodinger described basically an electron in a hydrogen atom as a standing wave with only whole number wavelengths allowed. he developed a very fun, again, back to peaking, mathematical model that describes this, which is by those symbols. You know, we should definitely skip that part of it right there. Those are what are referred to as wave functions. And again, it's a lot of sort of calculus derivatives and those type of calculations. But ultimately what we're basically moving towards, and we're moving away from with sort of these developments, is we're moving away from the idea of knowing, I think for sure electrons are moving around in these circular orbits that I can almost put my finger there and I know eventually the electron will come back around the circle again and I could find my electron just by, it's just a circular orbit, to this idea again that we really don't know exactly how they're moving or where they're at any given point in time. So a wave function describes sort of x, y, and z coordinates in sort of three-dimensional space, just like in math. You know, we sort of visualize these things in these three-dimensional sort of coordinates. And the idea is an electron is somewhere in these sort of three-dimensional space, and where they're sort of housed, again, is these ideas of orbitals rather than orbits. And we're definitely not going to get too much into this here. And again, there's a relationship, obviously, between sort of this wave function, the energy of the electron in the atom. So ultimately, sort of going through his sort of calculations, as I mentioned, we get to this idea of where we believe electrons are in the atom are in these orbitals. So this is basically where electrons are. And orbitals are not like orbits as in sort of Bohr's model where, like I just mentioned, you know, we know that this electron is definitely in this nice circular pattern. To really more orbitals are sort of probability maps. And they're kind of probability maps of areas in the atom where we would expect perhaps there to be a high probability of electrons being present, and maps where there would be, or areas where there'd be less of a probability. So sort of a really bad sort of drawing of this is if we sort of envision our nucleus here, and the red is sort of the high probability of finding an electron, we would expect a lot of pretty red, you know, near the nucleus, right? Again, there's the positive nucleus, there's the negative electrons. So, you know, there's a pretty good probability that we would find an electron somewhere near the nucleus. And if I change colors and I go kind of blue, as we fan out from the nucleus, you know, bluer areas may be a lower probability of finding an electron. Now, just because there's a probability of finding an electron somewhere in the atom, it doesn't necessarily mean that we know exactly how it's traveling or where it is at any given point in time. There's just a very good probability in this sort of red area that we would expect to find an electron there, not knowing exactly how it traveled, how it got there, or anything like that. And that's very different than sort of the orbit model where we have these distinct orbits where the electron is traveling around these nice circular sort of patterns that we know for sure eventually, you know, the electron's going to come back around. And I know for sure it is here because it's traveling these nice circles. So again, we move away from this model to this more probability model, which is based off of sort of Schrodinger's equations, and away from these circular orbits. So orbitals are not Bohr orbits. Again, his model not correct, works really well to describe sort of hydrogen, but unfortunately, as you get more electrons involved, it gets a little bit more complicated and doesn't really hold up. So orbitals are, again, these probability maps, and it doesn't tell you exactly how it's traveling or where an electron is, but again, there's a pretty good chance that, you know, if you kind of put your finger there, there's a good chance that you probably would find an electron somewhere in that area of the atom. Now, any orbital, as we're going to talk about here, any orbital, one important sort of aspect of it is an orbital essentially can only hold a maximum of 2 electrons. So any individual orbital that you got going on can only hold a maximum of 2 electrons. So sometimes we represent orbitals as we'll go around with like a line, maybe a box or something like that. And sometimes we represent electrons with arrows like this. And so if this was an orbital, the maximum number of electrons that it could be put in there is 2 electrons. We'll talk about why one's going up and one's going down here in a bit, but 2 electrons max that is the maximum number that you can put in any individual orbital. You don't have to fill it up with 2, but 2 is the max that you could get in there. So again, this was more of the Bohr's model, which is not so correct. And again, moving away from that to orbitals, this is sort of what we envision as an orbital, maybe a better picture than what I try to draw there. So this sort of red and dark pink is again more of a probability map of finding an electron. This darker pink color here is a higher probability. And as you can see, as you sort of fan out, the pink color gets a little bit lighter. And again, that means your probability of finding electrons are getting smaller and smaller. We sort of envision where I circled as the nucleus. You can see it's much higher in probability, again, of finding that electron closest to the nucleus. And as we move out, less of a probability of finding it. Again, even though there may be a high probability of finding an electron in a particular location, as we've been talking about, that doesn't necessarily mean that we know how it's moving, where it is at any particular given point in time. So they don't really have sharp boundaries, and we're going to talk about some different types of orbitals. And orbitals really are these probability maps, but you know, you can kind of think of them, they sort of are thought of as having certain shapes. So for example, this is an example was referred to as an s orbital. And an s orbital is thought of as being a sphere. So if you kind of like almost put some boundaries around it, you get this sort of circular sphere type of shape. And that is what's referred to as sort of an s orbital. Orbitals will have the same shape in the sense of all s orbitals, no matter what energy level it may be on, will always have the same shape. The only difference is as we go from one energy level to the next, they get larger. So as we go from, say, the first energy level, it's this nice little circle. Next energy level circle gets bigger. Second, third energy level gets bigger. Just kind of gets bigger, again, to sort of house all the electrons that would potentially be there. So can we really describe both the location and motion of electrons at the same time? And that's no, that's what's referred to as the Heisenberg uncertainty principle. Heisenberg uncertainty principle basically says the more you know about the location of an electron, for example, the less you know as to how it's traveling, and vice versa. The more you know about sort of its velocity and how it's traveling, the less you know about its sort of particular location. And that's sort of the wave function, and Heisenberg's uncertainty principle gives us no information detailed about its pathway. And again, that's why we oftentimes will think about electrons, you know, in this sort of random pattern around the nucleus, not really sure exactly where it's at, how it's moving at any given point in time. And really, the more you know about that, the less you know about the other aspect of it. Now, hydrogen has discrete energy levels. The energy levels are called principal energy levels. They're indicated by whole numbers, and that is, again, what this N refers to. This N is what is referred to as the principal quantum number, as I said before. There's actually 4 what are referred to as quantum numbers when we talk about this in reality. And in this class, we're not going to get into all that. When you take 1A, you'll get into it, but N is the principal quantum number. L is the angular quantum number. There's something known as M sub L, which is the angular momentum quantum number, and there's something known as M sub S. So these are what are referred to as the, this is the spin quantum number. M sub S, M sub L, L, and N are what are referred to really as the 4 quantum numbers. And they basically are sort of the rules are based off of like Schrodinger's equation and all those type of work that allows us to understand how many electrons there are in a particular place, how many orbitals there are in a particular subshell, and stuff like that. So, and here we're not going to get into specifically all of those guys, but there are what are referred to as sort of 4 quantum numbers. And again, n is the one we'll see a lot. And the easy way to remember n is, again, just more like sort of the energy level. So each principal quantum number basically is divided into sub levels or subshells. And on the first one, there is only basically 1 sublevel. On the second one, there's 2. On the third one, there's 3. On the fourth one, there is 4 different levels. So, for example, let's see here. If we look on the first energy level, the only orbital that's present is what is known as a 1s orbital. That's the only one present. The 1 means it's on the first energy level. The s is the type of energy level. On the second energy level, there is a 2s orbital. And there are 3 different, what are referred to as p orbitals. There are 3 different p orbitals on the second energy level. On the third energy level, there is also a 3s. There's also a 3p. And that is when we first start to see d orbitals appear. So in terms of orbitals, as we'll see here on this slide, there's s's, there's p's, there's d's, and there's f's as different types of orbitals. So a couple of terminology words that we've just saw, and just to make sure everybody understands, when we talk about something like a level, or sometimes referred to as a shell, a level or shell, we're talking about all the orbitals on a particular energy level. So what I'm putting in a box, this is what would be referred to as the n equals 2 level or the n equals 2 shell. Now, another terminology that is sometimes used is what we saw in the last one as well, is what is sometimes referred to as a subshell or a sublevel. Depending on your book, some people use shells or levels. And when we talk about a subshell or a sublevel, we're talking about a specific set of orbitals. So what I'm putting here in red, these 3 p orbitals is what is known as a 2p subshell or sublevel. I'm going to go with level since it looks like your book uses level. So we'll go with sublevel. And again, if we're talking about a 3D sublevel, it would be the set of 5 individual d orbitals together make up a subshell or sublevel. So level or shell is every single individual orbital on a particular energy level. When we talk about a sublevel or a subshell, it's a group of individual sort of orbitals that are together. Any questions on that there? So
Yeah, I have a question. Just, I'm confused what P signifies.
We're going to talk about that right now, I think, in these next couple of slides, but there are just some different types of orbitals where we would expect to find electrons in the atom. They're really these probability maps we've been talking about. So a specific type of sort of probability map is what's referred to as like an s orbital or a p orbital and so forth. So we're going to actually talk about those, I think, right now in these next couple of slides.
Okay.
Yep. Other questions? Okay, so let's talk about some of these labels. So as I mentioned before, for the most part, in any sort of electron configuration, this is sort of where we're going with this, is writing electron configuration and all this type of stuff. But pretty much there's 4 orbitals that I just put there, the s, the p, and the d. And the f are the 4 orbitals that you will use or may not use. And basically what they are referred to is they're really sort of different shapes. So an s orbital in theory has a different sort of probability map or shape than say a p orbital, than a d orbital or an f orbital. But ultimately all these guys are just hypothetical, theoretical areas within the atom as to where an electron would be found. Do they really have a shape of a sphere like this? They don't. As the previous slide said, there's no real good sort of boundaries for these orbitals, but it's thought of as s's being these sort of spherical ones. And as we'll see in just a second, a p orbital is more like a figure 8 type of shape, where in something like this, in terms of the s, these darker areas of pink are higher probabilities of finding an electron. So the first type of orbital that we have is an s orbital, and an s orbital on any energy level, an s orbital starts first off on the first energy level. So on n equals 1 is where you start to see your s orbitals start to appear, and they are found on every energy level. So 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Again, the number in front is the energy level. So if I say, hey, I have an electron in the 5s orbital, what that means is I have now gone to the 5th energy level, and my electron is theoretically sitting in this s orbital, which has a theoretical shape of a circle, basically, or a sphere. So one important thing to remember, especially for electron configuration, is in terms of s orbitals, there is only one type of s orbital, which means if you max out the s orbital, you can only put a maximum of 2 electrons into an s orbital. And here is a picture of sort of what an s orbital is thought of. Again, more of a theoretical sort of picture, if you will, thought of as being the sphere there on our x, y, and z sort of orbital. And again,
An s orbital has a spherical shape with the nucleus at the center.
And again, as he just said, that nucleus is thought of as being in the center. And as you sort of fan out, thus in that sort of areas where you would have a high probability of finding an electron. Now, p's, on the other hand, p's orbitals do not start until the 2nd energy level is where they start. So there is no p orbitals on the 1st energy level. They start at the 2nd energy level, as you can see, and continue up to the 7th energy level. And unlike s orbitals, there's actually 3 different p orbitals. There's 3 different types of p orbitals. There's the px orbital, the py orbital, and the pz orbital, as we can see here, x, y, and z. And as you can see down here, it's basically their location in 3-dimensional space. So we have one on the x axis, the y, and the z. And you can also see that it's more of a sort of figure 8 type of theoretical shape. Thought of as almost the nucleus is somewhere in this area. So again, high probability of finding electrons near here. As you sort of fan out, not so much here. Now, unlike s's, the p orbitals all taken together, the px, the py, and the pz orbital. This is what is sometimes referred to as the p subshell or p sublevel. Now, since each individual orbital could hold 2 electrons in a p subshell, you would technically have kind of 3 lines, if you will. And if you filled up all 3 of those p orbitals, the px, the py, and the pz, you could see that the maximum number of electrons, if you fill them all up, would be 6 electrons. So if you filled up the 3 individual p orbitals that start to occur on any energy level, starting at the 2nd energy level and above, you could fill them up by putting in 6 total electrons. And here's what, again, the p orbital looks like.
The 2px orbital is in the shape of a figure 8 along the x-axis.
And again, kind of where it all in the center there is sort of where the nucleus is thought. A little bit hard to see, but you know, the idea is more this area, probably higher probability, again, moving out towards the outer edges there, less of a probability of finding an electron. And there's the, and the z going the other way. So again,
the 2pz orbital is in the shape of a figure 8 along the z-axis.
And again, each of these technically could hold 2 electrons. So 2 electrons on this guy, 2 electrons on the last one, and the 3rd one. And again, that's our 6 electrons that they could hold in there. The next set of orbitals is what are known as d orbitals. And d orbitals don't appear until the 3rd energy level. So it is the 3rd energy level where they start. So you will not find a d orbital in the 1st energy level. 2nd, you have to get to the 3rd energy level. And then they have d orbitals, 3d, 4d, 5d, 6d, 7d. You will never get there. but 7d in terms of that. And unlike s orbitals or p orbitals, there's actually 5 different types, and these are them on the bottom. 1, 2, 3, 4, and 5 different types of d orbitals. For the most part, they look like 2 p orbitals that have been stuck together, except for the last guy, kind of like a donut in a p orbital coming through the middle. But since there's really 5 different d orbitals, each of them could hold a maximum of 2 electrons. So if I went through and filled up all 5 of them, that means that I would max out at 10 electrons for the d subshell. Again, taking all 5 of these individual d orbitals together is what gives me a d subshell. So the d subshell, all 5 of those individual d orbitals all together. And again, does not start until you hit the 3rd energy level. And here's what the d orbitals look like.
The 3D x squared minus y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes.
You get the same idea, I think.
The 3dyz or
The 3dz squared orbital is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z-axis.
So again, these things, will you truly see these shapes in an atom? You don't. Again, these are theoretical sort of probability maps of where you can find an electron, where they sort of drew sort of boundaries, so we do see those things as sort of shapes, if you will. The last type of orbitals that you have to deal with is f orbitals, and f orbitals really don't start until you hit the 4th energy level. So f orbitals don't start until the 4th energy level is where they start. And kind of like the other ones, there are 7 different f orbitals, and each of these are 7 different f orbitals. Again, in each of these orbitals, if we stuck our 2 electrons in and you filled it up completely, you will end up with a maximum of 14 electrons. So all 7 of these together, all 7 f orbitals, are what are referred to as the f subshell. And if you did fill it all up, as I just said, you would max out at 14 electrons. So 14 electrons is basically where you will max out. And if you fill them all completely up, you don't have to fill them all completely up. But if you did, you would max out at 14. So those are really the 4 sort of orbitals that we'll come across for electron configuration. S orbital, there's only one type of S orbital, and that means it starts on the 1st energy level, and on any S orbital you can only put 2 electrons total. When you get to p orbitals, they start on the 2nd energy level and above. Each p orbital subshell is made up of 3 different ones, a px, a py, and a pz. And if you max out the p subshell, you can put 6 electrons. D orbitals start on the 3rd energy level, and the D subshell is made up of 5 different D orbitals. And if you put 2 electrons in each, you can get 10 electrons to max out the D subshell. And lastly, on the 4th energy level, that is where we first see the F orbitals appear. And there are 7 different F orbitals that make up the F subshell. And if you fill that out, you could have 14 electrons. So that 2, 6, 10, and 14 numbers, really important for when we're writing electron configuration. All right. So in the wave mechanical model of the atom, electrons are probability densities diagrams where electrons are being found. These maps were, the electrons are most likely were developed by the mathematical analysis of Schrodinger, yes? All his funky equations. A lot of work to tell us, oh, I think an electron is like looking like in there, or those type of shapes, basically. So when we do go beyond atoms, the Bohr model was discarded because it really doesn't apply to atoms that have more than 1 electron. I say we talked about it works really nicely for hydrogen, but as we move away from hydrogen, not so much. So atoms beyond hydrogen that have an equal number of protons and electrons, they needed one more property to determine how the electrons are arranged, and that is spin. Electrons spin like a top. So there's a really important sort of rule that tells us when we look at an individual orbital. So again, I'll represent that with a line here. This individual orbital, whatever orbital it may be, a s orbital, a p orbital, d orbital, or whatever it may be. Basically what Pauli's exclusion rule says is that an atomic orbital is either an s orbital, a p orbital, a d orbital, an f orbital, can hold a maximum of 2 electrons, and those 2 electrons must have what are referred to as opposite spin. So if you remember, I said one of the 4 quantum numbers is the n sub s, which is the spin quantum number. And again, we're not going to get into too much of this, but basically it has 2 values. It could either be plus a half or minus a half. And basically when we sort of represent these orbitals in arrows, when we put the first electron into an orbital, it always goes pointing upwards. And that is what is sometimes referred to as having plus 1/2 for the spin quantum number. When we put the second electron in an individual orbital, we represent it by putting the electron pointing down. And what that represents is that that guy going down has a minus 1/2 for its spin quantum number. And again, a little bit outside of this class is that distinct little difference of having those electrons technically sort of spinning in opposite directions. And this sort of arrangement, when we do get electrons like this, 2 electrons going in opposite directions in an orbital, this is what is sometimes referred to as it being paired spins. So the electrons are thought of as being paired spins. Parallel spin is when they're both kind of going in the same direction. But there's what is sometimes referred to as Pauli's exclusion rule. It basically says that no 2 electrons in an orbital can have the same 4 quantum numbers. And that's sort of how you can get beyond the difference there is in the spin aspect of it. So one sort of spins upward, one spins downward, and that allows us not to violate that rule of no 2 electrons have the same quantum numbers, basically. And they would have the same quantum number, the same 4 quantum numbers, if you put both electrons pointing up or if you put both electrons pointing down. And this will never happen based on Pauli's exclusion rule. Again, because they're identical, these 2 electrons going in the same direction, up or down, they would end up with the same 4 quantum numbers, and that would violate his rule. So again, the way we get around that is in an individual orbital, electrons always go opposite spins when you put it in there. So you'll never have 2 electrons in the same orbital heading in the same direction. It can never happen based on Pauli's exclusion rule. So atoms have a series of energy levels, which is the principal quantum number, which is that n. The energy levels increase in value as you go up. So n equals 1, again, still the ground state or the lowest energy. N equals 2 and above. Excited states, as you go up in terms of that n number, you're getting further away from the nucleus, higher in energy. Each energy level contains 1 or more types of orbitals, and sometimes they're called sublevels or subshells. The number of subshells present is given by the n numbers. So again, n equals 2, there's 2, n equals 3, there's 3 different ones that are present. If you ever want to figure out quickly how many maximum electrons you can place in a level or a shell, there is a quick one calculation, 2 times n squared, n being that principal quantum number. So what that means is if my n is equal to 1, 1 squared is 1, 1 times 2 is 2 electrons. So that tells me on n equals 1, like the maximum number of electrons, if I filled up that entire shell, would be 2 electrons. If I went to n equals 2, 2 squared is 4, 4 times 2 is 8. When I get to that second energy level, I have my 2s orbital, and as we talked about, I have my 2p subshell present, and that is 2 3, 4, 5, 6, 7, and 8. Again, if I filled up that entire level. So this is sort of a quick sort of mathematical way. If you're asked how many electrons, if you max out an entire shell or level, you can do that calculation. Again, you square the n value first and then times it by 2. And it will tell you basically, how many maximum electrons you can put in there. Now, the n value is always used to label the orbitals of a given principal level, followed by the letter. An orbital can be empty. It can contain 1 or 2 electrons. So even though, for example, some orbitals may be available to certain elements, they may not have enough electrons to actually put anything in there. So they could have no electrons in an orbital. Just because you put 1 electron in an orbital, you don't necessarily have to fill it up completely. So you could have incompletely filled ones that have 1 electron, or an orbital that has a maximum of 2 electrons. Again, always going in opposite directions. And again, the first one in, always up, second one in, down in terms of the representation as to how you represent those electrons. Again, the shape of the orbital doesn't indicate the electron movement. The idea there, it's just a probability distribution of, I feel there's a good high probability somewhere in that orbital there could be an electron. Again, the Heisenberg uncertainty principle tells us, I'm not sure how it's moving, I'm not sure where it's at any particular point, but there's a good chance of finding an electron there. So the movements of a p orbital, the electron movements cannot be exactly determined. Electrons move within the 2 lobes of the p orbital, but never beyond the outside surface. Electrons are concentrated in the center of the node of the 2 lobes, and the electrons move along the outer surface. And the idea here is, still, we don't really know the movement of it. It may be true they're only moving with inside there, but we don't know exactly how they are moving in this particular case. So let's talk about a couple of ways that we can represent electron configuration. And electron configuration can be represented as we see in these 2 ways, which is 1s1 and an orbital diagram, which are arrows and boxes or lines. So when we look at something like hydrogen, hydrogen has 1 for its atomic number, which means it has 1 proton, and if it's neutral, it should also have 1 electron. So on the first energy level, as we've been talking about, there is only a 1s orbital. Electrons, when they go into the atom, go in the lowest energy level first, and they fill it up, and then they go to the next lowest and fill it up, and next lowest and fill it up. They continuously sort of put their electrons lowest energy to highest. So for our hydrogen, the electron configuration would be 1s1 is how it's worded. The first one is the energy level, or that n number. The s tells us that this electron is in a s orbital. And the very top one here tells us how many electrons are present in that orbital. So 1s1, and that's the way it should be written. 1 lowercase s and superscript there, 1 up on top. Our orbital diagram is either boxes like this or lines like I did here, where we label the orbital, and again, we use 1 arrow to represent each of the electrons. So as we just were talking about, the first arrow goes in the upwards position when you fill it in there. This orbital here, which is our 1s orbital, can hold a maximum of 2, so it does have room for 1 more. So for example, if we went to helium on the periodic table, helium is number 2. That means it has 2 protons, and if it's neutral, should have 2 electrons as well. And if we were to write the electron configuration for helium, it would be 1s2. And if we were to do the orbital diagram for helium, We could put one up and the next one would go down in our 1s orbital. So again, at this point, after helium, we cannot go any more electrons in there. We need to go to the next lowest orbital if we had more electrons to put in. Any questions on that there? Now, lithium would be 1s2, 2s2, I'm sorry, 1s2, 2s1. Let us talk about sort of something that's going to help us with electron configuration. And that is the actual order at which it goes in. And there's something that you can create on your paper really quickly to help you with that. And what we could do is, what we've been talking about is, on the first energy level, that is where s orbitals begin. And there are 2s orbitals, 3s orbitals, 4s orbitals, 5s orbitals, 6s orbitals, and 7s orbitals. Remember that when you get to the second energy level, that is where p's begin. So you go 2p, 3p, 4p, 5p, 6p, and 7p. Remember on the third energy level, that is where d orbitals begin. 3d, 4d, 5d, 6d. And remember on the fourth energy level, that is where f's appear, 4f and 5f. So this is something that you can recreate really easily, just remembering 1s, 2p, 3d, 4f. That's how they start. This is actually the correct order for electron configuration. And this correct order is used like so. You always start up here. And you basically just follow the arrows. So you do this sort of arrow move here. And this will give you the correct order as you keep zigzagging back. So you start up on top, you go down, you come back, you just keep zigzagging back and forth. The main difference though is what you see is the 3p orbital. Then the next one is actually the 4s orbital. And then you go back to the 3d. So this is a very big sort of difference that occurs. And that's why making this thing is really important for writing electron configuration. And that's because in terms of ordering, we have the 1s first, then the 2s, then we have the 2p. After the 2p, we have the 3s. After the 3s, we have our 3p, and then our 4s happens, and then our 3d happens in terms of the order. So again, electrons are just going to kind of fill in that thing just like that, this order. If you know this thing right here, or how to make it, which I just made it really quickly, and you can do that as well. And you know what we were talking about before, that you can max out an s orbital with 2 electrons. You can max out the p subshell with 6 electrons. You can max out the d subshell with 10 electrons, and you can max out the f subshell with 14 electrons. You could pretty much write any electron configuration you want to write. So for example, this is why when we look at the periodic table for lithium, which is 3, in terms of its atomic number, has 3 protons and 3 electrons. Starting up on top here, we have 1s2. That fills up my s orbital. Then I need to zigzag back to 2s1. In terms of its orbital diagram, it would have a 1s box, it would have a 2s box. First electron goes in, next electron goes down. First electron here would go up. Not drawn correctly in terms of energy, just to save room on the page here, but that's how it would look. We could also see we could put another electron in our 2s. So while we got some page here, I'm just going to go off a script here. So we'll go number 4 there on the periodic table, which is beryllium. And number 4 on the periodic table, which is beryllium, means it has 4 protons and also has 4 electrons, which means its configuration, again, you always start up here at the start, would be 1s2. We're going to zigzag back around to 2s2. In terms of its configuration or its orbital diagram, it would have a 1s box, it would have a 2s box, one going up, one coming down, one going up, and one coming down. So for example, why don't you do boron's electron configuration and carbons. So do boron's electron configuration, carbons, and do their orbital diagram. So again, always start here and continue on until you put in all the correct number of electrons. Boron's number 5 on the periodic table, and carbon is number 6. So 5 electrons and 6 electrons. Okay, let's take a look here. So again, starting at the top, we have 5 electrons to distribute. Always going to start up on top here. So we're going to go 1s2. Again, if you count the top number, that's now 2 electrons that have been placed in there. That's the maximum s can have. So I'm going to zigzag back and come to then after that 2s2. Again, if we count the top numbers, we got 2 and 2 is 4. And we still have more electrons, so I'm going to zigzag back around and come to 2p next, and it would be 2p1 in this case. Again, if you count the top numbers there, 2, 4, and 1 makes 5. If we were to draw our orbital diagram, we would have a box for the 1s, a box for the 2s, and because 2p, there's 3 different types of orbitals, we would have 3 boxes. This would be a px, py, and pz orbital. Again, these would technically be higher in energy. I'm just drawing them together. First one goes in here, second one goes down, first one goes in there, second one goes down. First one goes in terms of these ones where you have multiple orbitals left first in the upwards position. So that is where that guy would go, and that would be the orbital diagram. Again, typically you would draw it up in energy, but I just did decide. Question on that one there.
I had a quick question.
Yeah.
For the equation where it's 1s2, 2s2, 2p1,
Yeah.
do you have to put 1 above p, or is it okay if you just put 2p to show that it's just the electron?
This actually is one of the places where in chemistry where you do need to put the 1, actually, yeah. So you wouldn't just leave it empty. It's kind of one of the few places we actually do write the 1 in and stuff like that. Yeah.
Okay, thank you.
You're welcome. Other questions on that?
Yeah, I also have a question.
Yeah.
I'm just lost as to how we figure out the arrows.
Yeah, so the arrows, and we'll do carbon right now, and I'll kind of walk you through one more time. But the arrows, each arrow represents basically 1 electron, and each of the lines represent basically 1 individual orbital. So any individual orbital, that again, could usually sometimes be represented as a line or a box. The maximum number of electrons that an individual orbital could hold is 2. So when we fill up an individual orbital, the first electron is always represented by going upwards in there with an upwards arrow. The second one is always represented by going downward.
Mhm.
You put it in an individual orbital. Now, when we do have options of different orbitals here in a subshell, like in the P, there is actually a special way you have to kind of put them in. So why don't we do carbon, and we'll take a look at that one and how they get distributed in carbon, because there's a little bit of a difference because we do have some different subshells of sort of available, our orbitals available. So for carbon, if we did the electron configuration, again, starting up here at top, it would be 1s2. Again, that's going to fill that 1s orbital. We're going to zigzag back to the 2s next, 2s2. And again, if you count the top numbers, we have 2 and 2, which is 4. So that is filling our second one, zigzagging back now again to our p orbital. That is 2p2. And that would be 2, 2, and 2, which is 6 electrons. Now, in terms of this guy's orbital diagram, what I'm going to do is I'm going to steal the guy over here, I think. So his orbital diagram will look very similar to the guy before because it's almost the same. When electrons go in, again, they go in just like the order. So this is what's referred to as the filling order. So the first 2 electrons here are going to be on the first energy level, which is what the 1 means here. And they're going to be in that s orbital. So coming to our orbital diagram, we would put our first electron in upwards. Our second electron would go downwards in that 1s orbital. Our third and fourth electron is on the second energy level. That's what that 2 represents. And the first 2 electrons on the second energy level is in the s orbital as well. So that is what this guy would represent. First electron would go up, second electron would go down. Now, also on the second energy level, which is what this 2 here would represent, we have some more electrons. We have our 5th and 6th electron in the p orbital on the second energy level. And the first electron always goes in the far left here, and that's the px orbital. Now you have an option as to where you could put the next electron. You could put it in the same orbital, or you could put it in some different orbitals. And there's a rule which is known as Hund's rule. And Hund's rule basically says that the most stable arrangement that you could have for electrons is where we max out the parallel spin. So paired spin is when they're going opposites of each other. That's paired. Parallel spin would mean when they are going in the same direction. And the only way we could get them going in the same direction, as we talked about, we can't put them in the same direction in the same orbital. That violates Pauli's exclusion rule. So the second electron will actually go in here and then the orbital next to it. And then if you had a third electron, it would go to the next guy. And then on the fourth electron, it would start pairing up. So based on Hund's rule, this would be the correct distribution of our electrons. We would have 1 electron in the px orbital. We would have 1 electron in the py orbital. And again, if we want any more, we would put 1 electron in the pz orbital and then go back and pair them up. So when you hit a subshell, like a p subshell, a d subshell, an f subshell, when there are multiple orbitals that make up a subshell, they always go in one at a time, and then they go back and start pairing up if necessary. So that is how electrons kind of go into a subshell. S subshells is different because there really is not a subshell. It's any S is there's only one orbital. So the only way it goes in is the same way, up and then down. And that's sort of the same idea as to when you get the P's, they go in one at a time, upwards, left to right, and then back down and pair up. So that is how the electrons basically go into the atom one at a time in the upwards direction, and then go back and pair up in the opposite direction if necessary. So that's sort of how you place the electrons in those particular orbitals. Question on that?
Yeah, I got one.
Yeah.
So what does the exponent represent?
So the exponent in the electron configuration, like this guy up here, right?
Yeah.
So if we just dissect this, the first number is the energy level. And on that energy level, the S obviously represents the orbital it's in. And the number up on top represents how many electrons are in that orbital. So you could kind of think of like energy levels as different floors, like in a hotel, right? So like on the first energy level or the first floor of the hotel, there's only one room, right? One hotel room. And in that one hotel room, you can put 2 electrons. You go to the second level or the second floor of the hotel, there's 2 hotel rooms. In that first hotel room, which is an S, you can put 2 electrons. In the second hotel room on that floor, it's a P suite. And in that P suite, there's 3 individual rooms in there that each can hold 2 electrons. So you can kind of think of them almost like as floors in like a hotel, how many hotel rooms and how many kind of bedrooms in the suite as how many electrons you can kind of put in there. So you can see here with the carbon, we're only to the second energy level, but there's also electrons both on the second floor, if you will. You know, these electrons over here are in the S sort of hotel room, and there's 2 electrons to go in there. In our P hotel room there on the same floor, there's 3 individual rooms that could hold kind of electrons or people, if you want to think about it that way. So that's sort of the way you could kind of think of sort of these energy levels, these different orbitals. They're kind of like different locations within that energy level as to where you could kind of find electrons. Other questions on that?
Okay, thank you. I just have one more. It's just, what is the px orbital?
The px
How do-
orbital is what we saw that little picture of previously. It's an orientation in 3-dimensional space, like a map. There's x, y, and like a z sort of axis. So px orbital means that the p orbital is hanging out on the p axis in 3-dimensional space. Py means it's on the y orbital and on the y axis, and pz means it's sort of on the z axis in 3-dimensional space. So kind of like a map, that x, y, and z sort of coordinate, sort of a 3-dimensional sort of representation in space of sort of where it's at. Where, you know, we kind of think about the point where all those 3 axes come together is sort of like the nucleus. And, you know, that's sort of the 3-dimensional area in space of where those orbitals are located. And that's where we saw like the D or 2 of these kind of p orbitals together, where D has like, you know, x and y sort of orbital, dx, dy, and it's sort of like, you know, like a d orbital kind of looks like this. You have kind of an area of it's on the x and one that's on the y sort of axis in 3-dimensional space. Other questions? Okay, so let's stop there. And I think what we're going to do is, I think it's more important to kind of finish up this chapter here and getting through this stuff. So I think what we're going to do in lab, we're going to finish up this chapter and do a few more examples, obviously, on writing electron configuration and all that kind of stuff. So I'm sorry to say this, I think we're going to lecture again in lab, and we're just going to hold off on that experiment until we'll find a day where we'll do it, I think. So for now, just hang on to that experiment. And like I said, it's kind of an experiment that covers a couple different chapters. So we're going to finish up the lecturing here, and we'll talk about the exam that's on Wednesday and all that too during lab. Okay. So why don't we take a break, and we'll start when we start at 12:05, give her a chance to stand up and stretch and all that good stuff. All right. Make sure you put here in the chat if you didn't do so, and I'll see everybody like 12:05.